Hi, so today we are going to build up Lagrangian of quantum electrodynamics. So let's start. So we will start from the Dirac free Lagrangian and then we will see that how it transforms under a global phase transformation, and we will see. Okay, so this is Dirac free Lagrangian, and this is our starting point. Dirac free Lagrangian. Okay, so this Lagrangian is invariant under a global phase transformation if psi transforms like this. Psi and psi bar transforms like this. So okay, so if we have a transformation rule like this, transformation law like this, then this Lagrangian right here is invariant under the global phase transformation. But the things change quite a bit as soon as theta parameter depends on the position. So in particular, under a gauge transformation of this type, so the transformation, the Lagrangian transforms like the following. Let's see. Okay, so let's see if this theta parameter depends on position, and we try to transform our we try to see how it behaves. We can do like this. So d mu of e to the iota q theta psi. So we do the calculations using the chain rule. Q theta d mu of psi plus psi d mu of e to the iota q theta, and theta depends on position. So q theta d mu of psi plus psi e to the iota q theta plus these two terms and d mu of theta. Now if we take this outside, so we will get d mu plus iota q, and yeah, d mu of iota q d mu of theta. So here we get an extra term, and this term breaks this term breaks the invariance. Okay, so what we can do to solve this issue, I mean, this Lagrangian is invariant under a global phase transformation, but as soon as we consider this theta parameter to depend on position, so we go from global phase transformation to local transformation, so we get an extra term right here, and this breaks the Lorentz invariance. Okay, so to solve this issue, what we will do, we will use the gauge principle and we introduce a derivative, covariant derivative, which will have this form: d mu plus iota e q a mu. Okay, e q and a mu, these especially a mu is an auxiliary arbitrary field here, and q represents the charge and e represents the strength. That will be clear at the end when we will write the full Lagrangian. Okay, so now to solve the local invariance of this Lagrangian, we introduced a covariant derivative. Now let's see how this covariant derivative will solve our issue of local gauge invariance. Let's see. Okay, so let's do this. Let's see how this works. So d mu prime will simply be d mu plus iota e q a mu prime. Sorry for the sloppy writing. And psi prime transforms just like this. So to the iota q theta psi. Okay, let's do this. D mu of e to the iota q theta of psi, so we will apply chain rule on this term, plus I e q a mu prime e to the iota q theta of psi. So d mu of iota q theta psi plus d mu psi into the e to the iota q theta plus I e q a mu prime e iota q theta psi. Okay, so this will give us e to the iota q theta with these two terms and d mu of theta. And remember that theta now depends on position plus d mu of psi e to the iota q theta plus d2 I e q a prime of mu e to the iota q theta psi. Okay, let's take this thing out, and what we will be left with is, first write this term, we left with d mu, and here we will be left with d mu of theta plus I e q a mu prime and psi. Okay, now let's see how a mu prime, which was our auxiliary, or let's say arbitrary field, how it transforms. Let's see. So it transforms like this: a mu, sorry again, a mu minus 1 over e d mu of theta. Okay, Now let's put mu prime here in our equation and see where things are going. Iota q theta d mu plus iota q d mu of theta plus I e q, and let's write now our field 1 upon e d mu of theta. So here we will have some terms cancel out. I e q a mu, and when this terms, so we will get I e's will be cancelled out and it will be q d mu theta, all applying on side. So yeah, this term and this term will cancel out, so eventually we will get to be iota q theta d mu plus I e q a mu of theta. So we started from here. We started from this, and we had our assumption. We write our covariant derivative right here in this form, and after the calculations, because we wanted a covariant derivative which should be invariant under the local transformation, and its form was like this. So when we see that how this derivative, covariant derivative, will behave when we transform this, and under the transformation we saw that it has not changed. So if we take our auxiliary field in this, if it transforms like this, so finally we get we get a result which shows that if we take our covariant derivative of this form, so that will solve our problem of local gauge invariance. So far so good. Now we have our problem solved, which was the local gauge invariance. Okay, so now let's go back to the Lagrangian from where we started. So it was like this. It was like this, but this derivative was a problem because this Lagrangian was invariant under global phase transformation, but it was not working for local phase transformation. So we changed this with a covariant derivative of a specific form, and we saw that the form of this derivative was quite good under the transformation. So yeah, so finally we get a Lagrangian. Now we can write our Lagrangian like this, a very good Lagrangian which holds both for the local transformation and the global transformation. Okay, now let's write the full form, because the point of this video is to build up a Lagrangian for the quantum electrodynamics. Okay, so here we go. D mu plus I e q a mu. This was the form of the derivative that we mentioned earlier. Okay, iota gamma mu d mu plus iota e, and yeah, here we have some simplification. Iota into iotas will give us iota square, which will eventually be -1. So we simply get e, and let's write this q first, or let's write in the order in which it is. Q mu minus m, all applying on psi. Okay, so now we break our Lagrangian in two terms. We divide our Lagrangian in two parts such that we write iota gamma mu d mu minus m. So this part and this part together minus e q psi prime gamma mu a mu and psi. Yeah, looks good. Okay, so now if we look at our Lagrangian, which is developed so far, I mean, looks good now. So if you look at this, part, this was the Lagrangian from which we started everything. Yeah, we started from this Lagrangian, and that was actually, let's call this L naught, and this was Dirac free Lagrangian. Free Lagrangian means Lagrangian for a particle which is not under the influence of any potential anyway. And we get another term. Let's highlight this with this color. I don't know what is this color, looks orange. Anyway, this term is actually self-interaction term. Okay, so now we have a good Lagrangian, but there's one thing missing, and let's put that thing. And the thing that is missing is the kinetic energy term. Okay, let's build some more to get a full Lagrangian of quantum electrodynamics. Okay, so for our kinetic term, we can use f mu nu, f mu nu, where f mu nu is electromagnetic field tensor. So this term right here can serve as a kinetic energy term for our Lagrangian. So now our full Lagrangian will be let's write this as let's first write this kinetic energy term, mu nu f mu nu. Then we will have our Dirac free Lagrangian term. Sorry. Minus n psi minus, and the interaction term among the psi field and the mu auxiliary field that we introduced. Okay, now in order to describe the real physics, mu, basically this term, which is the interaction term, the interaction between the mu field and the psi. So mu field should describe a photon field. Okay, so now we have our full Lagrangian of the quantum electrodynamics. Okay, here E basically tells us the strength of interaction between psi and the mu, and Q is the charge of the field. We can also introduce a mass term for our Lagrangian. Basically, let's summarize this thing. Let's highlight this with green. Oh, sorry. Let's highlight this with green. So this is basically our Lagrangian of electro. Okay. We can also introduce a mass term for our gauge boson here, and yeah, by the way, gauge boson here is a mu field, which is a photon field. And we can also introduce a mass term here, which will be of this form. But by introducing this massive, a term for the massive gauge bosons, this term will definitely break the symmetry. But on a good side, luckily we know that the photon field, photons do not have any mass, so it's a good thing that photons are massless, so we don't need to add the massive term for our gauge bosons. So yeah, so that's why we are not going to add a mass term. So yeah, the problem solves itself. So yeah, I think this is it. This is our Lagrangian for quantum electrodynamics. See you next time.